Okay, so we've previously considered how we calculate the length of a line, length of a curve. And before we go to talk about curvature and torsion, they describe how the curve twists and turns. We're going to think about one more aspect of the length of a line. Okay, so let's think of a curve between points A and B. Okay, we saw that we can describe this curve in a parametric way. So we've got some origin O, and each point on the curve is described by some coordinate vector r that depends on some parameter t. And as we change t, this point kind of sweeps from A to B along the curve. Okay? And we saw an example of a circle of radius A. Okay, and each point on the circle is given by some vector r of t. Okay, and t we said was the angle between this vector and the x-axis. Okay, and we said to go right the way around the circle, we go from t equals 0 to t equals 2 pi. And that takes us right around the circle once. Okay, and in this case, our r of t, okay, was given by a cosine t, as the x component, and a sine t for the y component. Okay, but in the general case, this parameter t, so here we can visualize it easily, okay? It goes from 0 to 2 pi, and that takes us around the circle. But for this curve, the functions for x of t and y of t, so r of t will be x of t, y of t, and z of t. Okay, and I'm writing it like a column because I'm out of space. Okay, x component, y component, z component. So here, this is the x component, x of t, and here, this is the y component. Okay, in general, these functions will be quite complicated. Okay, in the circle, we know what they are. Okay, and they're not too difficult, a cosine t and a sine t. Okay, so we can define the circle, or any curve, through some parameter t. And changing t takes us, sweeps this vector in such a way that you will map out all these points on the curve. Okay, but there's another, hopefully obvious, parameterization, and that's the length of the curve to a certain point. So if we start at point A, then each of these points is uniquely defined by the distance they lie from point A. Okay, so this point here is this distance from point A. This point here is this distance from point A. This point here is the length of this section from point A. Okay, and this point here is the length of this section from point A, etc. I can't remember which one I pointed to, this one or this one. Okay, so if you start at point A and you know the shape of your curve, and you say, my point is at 10 meters away. Okay, well that's this point here. Okay, or my point is at 5 meters away. Okay, well that's this point here. And it's unique. No other point is 5 meters away from A. Okay, so we want to make this a bit more rigorous. So we said that the length between 2 points A and B was equal to the integral of ds between those points. And ds, remember, is we split up our curve into little infinitesimal segments. Okay, so this is abstract, but we know, we found what ds was. It's the magnitude of the derivative of r of t dt. Okay, between ta and tb. Okay, so ta is the value of t that puts us at point A, and TB is the value of t that puts us at point B. Okay, my blue pen's rub it running out, so I'll switch. Okay, so at this point we can define the arc length function. Okay, and we're going to define it as this function s, and it depends on the parameter t. Okay, so we still have this parameter t. And it equals, we're going to just have this thing again, r prime of t dt, but between different limits. And we're going to say that ta equals 0. Okay, so that's kind of our starting point. 0 to t. Okay, and because we put the upper limit as t, that's taking us to this general point. Okay, r of t. And because we've got this upper limit, we need to call this t something else. Okay, so this is a dummy variable that we integrate over, so we can call this whatever we want. So let's call it tau. Okay, so what I did there was basically say that the integral of x dx can be written as the integral of dog d dog, okay, or the integral of cat d cat, or the integral of qub d qub. Okay, doesn't matter as long as this variable or symbol is the same as this. Okay, so this is the same as this is the same as this is the same as this. So hopefully that's clear. Okay, you can call this anything you want if you're going to integrate over it. Okay, so this thing is none other than the length of your curve from point A, which corresponds to your t equals 0, to the general point given by r of t. Okay, so let's think about that a bit more. Maybe let's look at the circle as the example. Okay, so for the circle, our r of t was a cos t, a sin t. Okay, so for the circle, r prime of t, which is this thing, is equal to, so we did this before, minus a sin t, a cosine t. Okay, and its magnitude is equal to the square root of a squared sine squared t plus cosine squared t. Okay, which equals, so this thing is 1. So this is the square root of a squared, which is just a. Okay, so that means that for the circle, this s of t function is equal to the integral from 0 to t of a dt, which is just, we can bring the a out front, integral, oh yeah, we're going to call this tau. Sorry. So this is a d tau from 0 to t, which is equal to a tau from 0 to t, which is just equal to a times t. Okay, so for the circle, s of t equals a times t. Circle of radius a. Okay, and we can think about the circle. If we go from t equals 0 to t equals 2 pi, t equals 0 implies s equals 0, and t equals 2 pi implies s equals 2 pi a. Okay, and what is 2 pi times the radius? It's the circumference of your circle. Okay, so this s really is a measure of your length. So this is t equals 0. As you go right round the circle. You go round by 2 pi if it's t, or in length you go round 2 pi a. Okay, so this point on the circle corresponds to t equals pi over 2, or s equals pi a over 2. Okay, so a quarter of the circumference. This point is the semicircle length, so that's s equals pi a. Okay, and every point in between can just be defined by the value of s, that is the length from this point to the point of interest. Okay, so this point here can be defined by s equals 3 pi a over 4. Okay, so there is this natural parameterization, it's called, which is describing the points on the curve by this kind of function s, or this length from the start point to the point of interest. Okay, and you can re-parameterize your curve in terms of this s. Okay, so here s is at, so we can just as well write r of s. Okay, and maybe let's do that. To finish off. Okay, so this means that we can write r of s, okay, not the parameter t, we're not going to use the parameter s, equals a cosine, what's t? T is equal to s over a, cosine s over a sine s over a. Okay, and this is a circle parameterized in terms of the natural parameter s, okay, where s, let me do this, okay, where s goes from 0 to 2 pi times a, the circumference of the circle. Okay, so we're going to use this kind of s function in what comes next. So in general, it's quite difficult to calculate this s. Okay, so it's not always easy to write this natural parameterization. For the circle it is, okay, but in general it's not. Okay, fine, okay, let's move on.